Okay, so our next speaker is CS Rajan from Ashoka University. Will talk to us about equidistribution of matrix-valued Gauss sums.
Okay, so thank you. Thanks the organizers for the invitation. It's a great pleasure to be back here, and so I'm missing many of the talks because of real teaching schedule and such things. I do hope that ICTS keeps this conferences and workshops in more regular times where many more people can come and join this. Okay, but still, it's a great pleasure to be back in ICTS, to be able to give a talk. Okay, so let me define the following. So what we are looking at is Gauss sums. So we recall the definition of Gauss sums. So we are taking P is a prime, and we are looking at Fp is the finite field. And Q is some P to the power A. And, so we have FQs, FQ is the finite field of Q elements. And we can take so I'm going to define, Gauss sum is defined with respect to, there's a chi is what is called a multiplicative character, FQ star to C star character. And we take an additive character psi, say from FQ, we can take the trace to FP, the trace map. And from FP, you can take a additive character to C star, for instance. You have a map from Z to FP. You can send the X to e to the power 2 pi I. X by P. Yeah, I might put the index psi q or just make it psi, meaning I'm having some additive character which is defined. So I might drop the subscript at many places. So the Gauss sum or the multiplicative character is defined as a summation of chi x times psi of x, x is in FQ star. Yeah, so it's kind of appears, it's ubiquitous or whatever it is in many places, and satisfies a lot of remarkable properties and analogies. So let me list some of them, just because it's kind of interesting and it's nice to go through some of these properties. Okay, the first thing, just before I talk about the motivation for Gauss sum or whatever it is. So one property is that the absolute value of the Gauss sum. I'm not going to list all properties which the Gauss sum satisfies. I'm just going to say some, which is of interest. So the absolute value of Gauss sum square is equal to Q if chi is non-trivial. Of course, if chi is trivial, then the sum is summation of the additive character, and that's -1 or whatever it is. Okay. So this is not too difficult to prove that it has what would be called a purity property. Okay. Yeah. So the first time the Gauss sums, it's also was probably considered by Lagrange and called a Lagrange resolvent before Gauss. But the reasons for Gauss to consider this Gauss sum was initially apparently when he wanted to construct a regular n-gon. And one knows that the cases to be considered are when n is a Fermat prime. And so it's 2 to the power some a plus 1. So what you want to do is when you want to construct the nth roots of unity to get the regular n-gon, so you will have to do it in a successive quadratic stages, right? And so you will have to locate the quadratic subfield sitting inside your cyclotomic field. So both for construction of the regular n-gon as well as for is proof of quadratic reciprocity. A later proof of quadratic reciprocity. What you need to do is to locate the quadratic subfield says some L or whatever, say Q zeta P. This is of P is odd, it's degree P minus 1. So that's even, and then there is it's a cyclic group, the Galois group. So there is a unique quadratic subfield which is sitting inside. And the basic point is to, you just, this is Q, and you have H, and you average with respect to H. And then you basically you get what are called this quadratic Gauss sums of zeta P. Average with respect, take the average with respect to this Galois subgroup, which is the Galois subgroup of Q zeta P over L. And you get your quadratic Gauss sum, and so that allows you to get the field which is there, this quadratic subfield. So, but this is also needed for the later proof of quadratic reciprocity when you want to figure out what this quadratic subfield is. Okay, but the second thing which I would like to say is the analogy with Euler's gamma function. Sorry, the first talk will be somewhat very elementary, so I hope you. Yeah, it's okay. Good. So recall the Euler's gamma function gamma s is integral 0 to infinity e to the power s e to the power minus t dt by t. And so if you fix s, say s is, if you have to probably take real part of s greater than 0 or 1, whatever it is. Yeah. Safe for. So if you fix s, the map t going to t power s, this is a multiplicative character, or rather character of r star positive. And the map t going to e to the power minus t is an additive character. Of r under addition, this is under multiplication. And dt by t is the invariant measure. Measure on r star positive. Right? By this one means that d of it's invariant under multiplication. Okay, so the Gauss sum has can be thought of in analogy with the gamma function, or more generally L functions or the epsilon factors. So the analogy can be. I'll state one more. Is that so the gamma factor, of course, you can see is a factor which you attach to a Dirichlet characters or modular forms, various types of gamma factors in order to get functional equation. So, so the analogy in some sense, you can think of the Gauss sums as like gamma factors at the various primes p. So for that, let's look at one more thing, is the functional equation of Dirichlet characters. Of Dirichlet functions. So we take again, say, let's take chi to be a z naught p z star, which is of course isomorphic to the Galois group of u zeta p over q. So you take character. Now we would be thinking of this as a Dirichlet character, and you can define an L function LS chi. Yeah, I can define it in more general, but let's just, so product over L naught dividing P of 1 minus chi L by L to the power S. Maybe for real part of S greater than. This product converges and so we complete it just as to a complete it with by adding factors at infinity on the conductor and things like that. So I suppose lambda is chi. Where is it? I think it's u by pi to the power s plus a by 2 times. So this is like Q is like the conductor, or rather this is P, sorry. P by. So the conductor which you are working with, what is A? A is equal to, put A equal to 0 if chi is an even character, and 1 if chi of minus 1. And if chi is an odd character. And what you have is a functional equation is lambda of S chi is epsilon chi times lambda of 1 minus S chi bar. Chi bar is a complex conjugate. And what is epsilon chi? Epsilon chi is a Gauss sum. And here I'm always a bit puzzled about the presence of I, which I to take and whatnot, but maybe it doesn't matter, times square root of t. There's the sign of the Gauss sum. This is basically the sign of the Gauss sum. Yeah, so if you look at Tate's thesis and other things, so then this epsilon chi basically breaks up as a product over the factors, various prime factors, or various ramified prime factors. You have to use an additive character in order to define the local factors, epsilon chi's. And that's how this additive character comes in. Although here I'm suppressed the use of additive character. But anyway, so in some sense, maybe my one justification for talking in a conference on rational points is that the Gauss sums or the signs of the Gauss sum gets related to the root numbers. And the root numbers, of course, control if you're working with self-dual representations or other things, then the root number is plus minus 1, for instance, elliptic curves. So then the vanishing, or if the root number is plus 1, minus 1, then it forces the L function to have a 0 at the center, and which means there exists at least a rational point and so on. So probably a justification for being in this conference, but anyway, that is. But still, thanks, irrespective of all this. Yeah, so the Gauss sum has this role where it's kind of the analogy with L functions and epsilon factors is kind of very nice. So to keep in mind when you come across some questions or issues which are there. Yeah. So yeah, right. And of course, the Gauss sums are related to Stickelberger and all, but I will not talk about that. The kind of results I want to talk about right now is the starting point is done by. So I want to talk now about the equidistribution of Gauss. So talk about equidistribution. Of Gauss sums. So the theorem is to this Delin. Again. So what Delin's theorem? I'll explain what is equidistribution. So what Delin proves is. So what you would like to look at is so we know that the normalized Gauss sums. So we know that the normalized Gauss sums for the non-trivial. So they belong to S1. They have absolute value 1. Absolute value 1. And what Delin says is that if I look at the set of Gauss sums G chi psi, so maybe I should put a chi, maybe psi q, so that the thing as chi runs over all multiplicative characters of FQ star to C star, very non-trivial. So these are subsets of S1, and so these subsets are equidistributed as q goes to infinity. So either as p power n, p power a, or whatever. As just q goes to infinity in whichever direction. These sets are equidistributed with respect to the normalized Hermitian. On the unit circle. Okay, so what you are saying is that so these are absolute value 1. These are some sets, and they are just spread out in a uniform manner across the circle S1. So what does equidistribution? So let me just recall the equidistribution. Equidistribution. So you have some collection of, say, you have a set X, maybe with locally compact Hausdorff probability measure, say mu x equal to 1. So some set, and you have some collection of subsets for every n greater than equal to 1. You have a collection of subsets, say finite subsets, Sn is finite. Sn is finite. And you would like to know when this, okay. I don't require mu x equal to 1, but anyway, so what happens is for any subset A, measurable or whatever it is, for any subset, you can consider the number of the intersection of Sn intersection A and divide by the number n, cardinality of Sn. And now what we would like to do is to consider the limit as n approaches infinity. Okay, first of all, I think I don't need a measured mu to start with. In some sense, if you have such sets, then it gets equidistributed with respect to some measure mu, which is the limiting measure. So if this is equal to the measure of the set A, in the sense there exists a unique measure mu which has this property. Conversely, if you have given a measure mu to start with, then you would like to say that the sets Sns are equidistributed with respect to this measure mu if this property holds for all A. For any subset, this property holds. So that would what is the name notion of equidistribution, that you count the number of points which hit A, the average number of points which hit A, and that should be almost equal to the measure of A. Yeah, for instance, the Cherepanov density theorem will say something like equidistribution of the conjugacy classes. Yeah, but equivalently, one can, so the equivalent notions are, if X has some topology and such things, you can look for F continuous functions. If F is continuous on X for all continuous functions, for all with maybe compact support, what, yeah, any compact support or whatever it is. So you would like to say that the summation of, instead of, this is like the indicator function on A, whereas now you would like to look at continuous functions f of xn, where say f of x belongs to Sn, 1 upon cardinality of Sn. So now instead of the indicator function, this is like indicator function for A, but right now I work with f is continuous functions, and then let limit n goes to infinity. So if this is equal to integral 1 by f d mu over x, then we say that these Sns are equidistributed with respect to this measure mu. So that is saying Sns are equidistributed with respect to mu. So the advantage of going to continuous functions or some is to, you can choose a nice basis for the space of continuous functions with respect to the topology of uniform convergence. So for instance, when X is a group, say compact group for which you would like to talk about invariance with respect to the Haar measure or anything. So you can restrict your attention for the basis. You can restrict attention to characters of irreducible representation. Irreducible representations of G, which you know by Fourier orthogonality that the integrals are all 0. So what to say that, so when in this case, so when X is equal to G, a compact group, okay, and we are taking mu as a Haar measure, normalized Haar measure, right? So then equidistribution, if I take the trivial character, then basically that's just counting upon the number of points, so that's not the same. So equidistribution amounts to saying with respect to mu is amounts to saying that for any character for any irreducible character chi of G, that means the character of some continuous representation to some matrix group GL and C. This sums are 0 because the right hand side is 0. So what you would like to show is that limit as n goes to infinity, 1 by cardinality of Sn, summation chi of x, xn Sn. So this should be 0. If you take any irreducible character chi of G, chi not equal to 1. For the trivial character, of course, it's measure, so it has to go to 1. So that is anyway the counting measure which you have. So the equidistribution with respect to the Haar measure is an extremely simple formulation if you are working with compact groups and looking at irreducible. So all you have to say is for any non-trivial irreducible character, the average sum goes to 0. Okay, so that is, so if I take, for instance, x equal to S1, and what you would like to say for the Deline's theorem is to say that, so there are basically the number of non-trivial characters, FQ star is Q minus 1, so you have Q minus 2 characters, non-trivial characters. So you would like to say that 1 by Q minus 2 limit as Q goes to infinity of this normalized Gauss sum. So maybe divide by square root of Q, G chi psi is equal to 0. G chi psi, so the irreducible characters, so from S1 to S1, the non-trivial characters are Z going to Z power n not equal to 0. Right, so you'll have to say G chi psi power n equal to 0 for all n not equal to 0. So this is what you have to show in order to say that this Gauss sums are equidistributed with respect to the standard measure on the circle. So we can, now one can say what, so the idea of whatever Deline's proof is the connection with Kloosterman sums. So basically the Kloosterman sums are whatever, I don't know whether it's, if I'm to look at the nth moment, the Kloosterman sums are like, is it the kernel function? I don't know, yeah. Anyway, so one can define the Kloosterman sum. So what you get is that, let me say this, that if I take the nth moment of a Gauss sum, so that is A belongs to Q star of chi of A. So it's I don't know how to think of it, whether you think of the Fourier transform of the character chi with respect to the Kloosterman sheaf or anyway, there is some. Well, the Kloosterman sum is the sum along hyperplanes, summation product xi equal to A of, it's a mix of the additive and the multiplicative. So getting this identity is not difficult. It's not just a rearrangement of the sum. So what you have is that this is the Kloosterman sum, which, yeah, I don't know in what context it originally came up. Maybe, yeah. So what you have to do so it's not too difficult to show that a bound for the Kloosterman sum is, this is easy, just like you have an easy estimate for the Fourier quotients of cusp forms, which is, I think it's q to the power n by 2. But so the key to Deline's theorem, the proof, so let me write it out here. I've rubbed it off. Oh, I said this. Okay, this is the theorem of Deline. So what you have to, so the estimate, the key estimate is that what Deline shows, and surprisingly not at all easy. It depends on the full force of veil 2, but not elementary, is less than equal to, or yeah, n times q to the power n minus 1 by. So there is a shaving of half. You shave an exponent of half, and that is crucial to getting this equidistribution result. Okay, so that is classical theory, well understood. And yeah, there are some, apart from Dellin's expose in SGF 4.5, there are books by Katz, and there's also a Bourbaki article by Fresa on general equidistribution problems, the recent. Okay, so then what we are interested in, so let's say what we are going to be interested in. Yeah, a lot of what I'm saying is, okay, I should have said my work. Whatever I'm saying is joint work with Samir Kulkarni. I should have said it in the beginning, but I forgot. Anyway. Right, so what we are interested is in looking at generalizations of Gauss sums. So as I read somewhere that Emil Artin and the German or the Berlin number theory school are interested in defining more and more L functions and Gauss sums and other things, other such aspects, trying to figure out the properties. So this was defined by Lamprecht in 1956 or so, and some of its properties studied. So the point is that you can look at FQ star as sitting inside FQ. So this can be thought of as GL1 FQ. And this is to be thought of as 1 cross 1 matrices M1. So you can do a similar thing. So what Lamprecht looks at is, you look at the matrix group GL and GLD, say, FQ, and you consider irreducible representations, rho, to some huge, maybe, okay, GL and C. So rho is some representation, and then you can define as usual. So for a character, I look at GLDFQ is contained inside D cross D matrices. And here we can take the trace to FQ, and of course trace to FP. And so here we have again a character psi, an additive character on this. So then you can define as usual, but this time it is what is called a matrix valued Gauss sum. So define the Gauss sum G rho psi is summation rho x psi of x, where x is in GLDFQ. Okay, so this is, of course, this is a M cross N matrices or complex numbers. But if easy to see, if rho is irreducible, then G rho psi is a scalar matrix. Identity. The scalar matrix, this is scalar. And the purity property for this was given by Kondo. Purity was proved by Kondo around 10 years later. So the point is that although you define it, you would like to know what these irreducible representations are and what the characters of this irreducible representation. So this was done in a very path-breaking work by Green in 1955 also. So where he classified all the irreducible characters of general linear group or finite fields in terms of conjugacy classes. It's one of the, apart from the symmetric group, you have maybe the only other group where you have an explicit parametrization of the irreducible representations in terms of the conjugacy classes. So anyway, what Kondo or this thing showed using Green's work, so using Green's work, that there is a purity for this result, 0 psi, for the scalar, which is of the form q to the power. So there is a d squared, but there is a deficiency kappa rho by 2. Where what happens is kappa rho is as I said, the irreducible representation of the parameters by conjugacy classes. So you look at the generalized multiplicity of 1. There's a generalized multiplicity. That is a unipotent, the number of unipotent elements, or the multiplicity of 1 in the characteristic polynomial. One in the conjugacy class equal to multiplicity of 1 in the characteristic polynomial of the conjugacy class. Okay, so that's some deficiency, but okay, so that is the aspect which one is there. Point is that again, of course, one can ask why are these Gauss sums of relevance or whatever it is. So before I go on to what our results are, let me just say a bit about this Gauss sums. Not, I hope. Yeah. So, yeah, one aspect where they seem to be involved in current work of people like. So this is what would be called beyond endoscope. I should say I don't understand most of these things, but I'm just stating it in case other people are interested, they can. So the point is that one can define L functions of modular forms or other representations, maybe for the regular representation of a symmetric square or Rankin-Selberg, and in some very limited number of cases where you can define the L functions, whereas the conjectures of Langlands expects that you can define L functions for far more generally, and knowing their properties would be helpful, for instance, in doing Ramanujan or many other things. So what I suppose Langlands started off was trying to figure out a way of defining this, and as Kasselman said in a lecture in TIFR, I don't think anybody really understood what Langlands had to say, maybe including Langlands. It was apparently too extremely difficult on this. Of course, that doesn't mean people are not working on it. So the work of Brauman and Kazan before that's around the turn of this. I'll just list some names which are there. Around 2002 or something, then paper by some work of Naubau, Chow and others, and Lomo, Letelier. The point about all these things is that, yes, we want to understand beyond endoscopy, but it's too difficult. Easy toy model is to check our conjectures or ideas against groups or finite fields, where you can try to get the algebraic geometry or the required things over there. So for them, this is a toy example to work with and try to see whether the conjectures work out in whatever way it is. So that's exactly what the things are. It's just to verify. It's a verification process about what the things are. The point is, it's still, there are things which are unknown even for groups or finite fields from the way where conjectures are there. The conjectures of Braum and Kazan or Nobochov on these aspects. Yeah. So there is some things, but of course it's a heavy machinery of all kinds of algebraic geometry which is brought to the bear on this problem. So among other things, what although I stated the purity result like this, so both Kondo's work and Braum and Kazan. So Kondo and Braum and Kazan. So let me restate the purity in the following form. The point is that this Gauss sum, it reduces to an abelian Gauss sum. 0 psi reduces to an abelian Gauss. So, okay, so the point is that when you redo, so Green's work is redone by Deligne and Lustig. Except that, so if you look at what are called the cuspidal representations, see, okay, so, no. Cuspidal representations of GLDFQ, those, for instance, representations which have invariant vectors, the invariants with respect to the unipotent groups are all trivial. Then they are parameterized by a collection of characters, say chi of some maximal torus. So, or rather, let me not say cuspidal representation, just representations of GLDFQ. So you take a torus T, contain it's a maximal torus inside GLDFQ, and you look at parameters by characters chi of, so T is some whatever it is to C star. So you can think of it as RTG. It's what is called cohomological. This is what is the process of cohomological induction also. Anyway, maybe to cut a long story short, point is that if I take this row, is of the form cuspidal representations RGT chi, where chi or cuspidal representations from FQ to the power D star, which is sitting inside. Let me say, you can make it sit inside GLDFQ. And chi satisfies the property that chi is not equal to chi cos chi sigma. The sigma is a Frobenius, generator of the Frobenius. Sigma generates the Frobenius. The Galois group of FQ power D. Okay, so when you say it in this way, then what happens is that the Gauss sum 0 psi, this is basically up to a factor q to the power d squared minus d by 2, the Gauss sum of the character chi psi. So here chi is sitting inside GLDFQ, psi is the same character from matrices to trace to FQ and then push it. So you form the same Gauss sum as before, but for the torus now, maximal torus. Instead of GLD, you're forming this. So this is really an abelian Gauss sum. And so if you have trivial characters, that causes the drop in the. So okay, so what happens is, if you put all these things together, so the first theorem is kind of obvious. That if you look at the normalized, so the normalized Gauss sum, the value will be q to the power d by 2, because this will have q to the power d by 2 and d squared by 2. So the normalized Gauss sum of cuspidal representations, irreducible cuspidal, of GLD of Q, or equidistributed with respect to the Haar measure. Haar measure on this one. It's not too difficult. It's basically a counting argument that this the number of such primitive characters or whatever it is are large enough that they dominate the set of all characters of the torus. And so that's a very simple counting and with whatever I've said so far, this theorem follows without too much difficulty. Right? Okay, so then it follows. So let's try. We thought we'd play around a bit. So now let's try to work with the group PGLD, which is GLD modulus center with Q star. So here what you're looking at is representations which have trivial central character. So rho has trivial central character. So in the parameterization of Deligne-Lustig, it's not too difficult to say. So rho chi, suppose. So that's the same as saying this character chi is trivial restricted to Q star fitting into the torus. Okay, so you try to work for trivial central character. The answer is the same when d is greater than or equal to 3. It gets equidistributed with respect to the Haar measure on the unit circle. But what happened? We got to see that when d equal to 2, the answer is different. Yeah, so when d equal to 2, this normalized Gauss sums actually only take the value only plus minus. Only plus minus 1. So that's so in fact we can say exactly, let me just say what the answer is. In fact, one can say in this case almost precisely half the number, exactly which ones takes the value plus 1 and minus 1. And I will just say what its relation with, but let me say the answer. What is the answer? So what happens is, so you're looking at FQ squared star, and that is sitting inside GL to FQ. This is a non-split torus. And so this has elements Q squared minus 1, the cardinality. And you're looking at characters which are trivial on restricted to FQ star. So when you divide by Q minus 1, so you get Q plus 1 such characters. When Q is odd, this is even. And this group is the collection of such characters, the group of such characters is cyclic. Yeah, actually what happened was, yeah, I should say, okay, we got to this result and then later realized that it ties up with the results of Froelich, Koiru and Deligne on Serre and Serre, Froelich, Koiru and Deligne on root numbers of self-dual representations. But let me just say what the result, which was also there in Froelich, Koiru and Deligne. But it's fairly cyclic. So what happens is, if you know it is going to be plus minus 1, this group has so it has two subgroups. It has subgroup of squares and non-squares. And what you have is, so you choose, so what you do is you choose a delta in FQ star, which is not a square. So then FQ squares is equal to FQ attached square root delta. It doesn't matter. So then what we get is that the normalized Gauss sum equal to, so this is theorem or whatever it is. Okay. So let's say theorem. It's equal to plus 1 if chi of square root delta equal to 1 minus 1 if. Okay, so that would be there in the FQ squared star. Okay. So yeah, so this proof is, so yeah, so let me just say the connection with the work of Serre. Most of what I'm saying is, this is not too difficult, the theorems, but to prove, just that it was, and Deligne. So I think what Serre conjectured is that you look at a number field or a function field, a global field, let's say K is a global field, K over L over K global. It's a global field. And you take a, so you take a representation of the Galois group L over K, Artinian representation, GL and C, and you would like to look at the root number. So if the character is real valued, character psi rho x is real valued, then one can say the whatever, so there is a root number which you can attach, the Artinian, the Deligne-Langlands root number or whatever it is. The root number belongs to plus minus 1, takes values in when the character is real valued. But what Serre conjectured is, sorry, this is in general, that is the thing, that if the representation, if rho itself is, so conjecture of Serre, and if rho itself is definable over reals, rho definable over reals, or R, then this should imply the root number is 1. And he proved it for function fields using the Grothendieck formulas. So what Froelich Koiru did independently is to prove this conjecture by basically reducing it to the reducing it to the local case. This is only true for global fields. The local fields, the root number or local fields, if I take, even if it is definable over R, the root numbers can take plus minus 1. It can be, the signs can be there. And what Delin does is to reinterpret in a very beautiful manner, very efficient manner. It's still, I can't say I understand these things, but in a sense, the product of the signs being plus 1 amounts to a kind of Hilbert reciprocity. And the main case for him is to reduce to the dihedral case and prove this. So once it's a very kind of probably cure do a case by case reduction, but Delin does it very beautifully and just gets to this kind of thing. Our argument is very simple, but we don't have any relationship with, so far with these aspects. Okay, so this we did, but then we missed out, or we didn't see immediately that the results we had are really can be done in the self-dual case, more generally in the self-dual case. So what happens is, so instead of GL2, we can show now that you look at hospital self-dual representations, but now of arbitrary degree. And for self-duality, for having non-trivial representations, the representation degree should be even. So you are looking at GLD FQ. To some GL, say 2n of complex numbers, but these are self-dual representations. That means the representation is isomorphic to its contrarian. And here again, you can show that the normalized Gaussians are equidistributed with respect to plus minus 1. But in the sense, the dominant case when you are working with will kind of reduce to this case for the count, but it's not always true, or rather we can't say exactly when something is plus 1 or minus 1. But since the dominant case dominates as far as equidistribution goes, this result comes out by this. Yeah, so that is what I have to say. Yeah, but these root numbers, of course, get related to the what would be called the automorphic root numbers. So if I look at just a minute, I don't know how much time I have, but so you can look at, if I look at GLD, say ZP, so that GLT of SP, and you can look at irreducible representations. Think of it as an irreducible representation out here and do compact induction. That way you get the cuspidal representations of GLD QP. But you can look at so what you get is that somehow if I'm looking at self-dual representations, tamely ramified, so then this theorem should say that the root number should be equidistributed between plus minus 1. I'm not saying we have written it down, but that should be true. What also is not clear is, for instance, what is the geometric meaning of, that the root number is plus 1 or minus 1? Whether does that mean that this representation lifts to, saying it's a self-dual representation means it goes into some orthogonal group. Whether that means it lifts to spin group, or is that the correct way to look at it? But we don't know yet. We don't have those kind of results. Maybe it's simple, maybe it is not, or it's known, we don't know. Okay, so that is what it is, and it also gets equidistributed so that if I look at root numbers of tamely ramified self-dual representations, then the root numbers are equidistributed with respect to plus minus 1. Most likely that should follow from this kind of stuff. But if we have representations which are more highly ramified, I suppose those root numbers are related to kind of Gauss sums, but not over fields, but over rings. Yeah, but I don't know what the state it is. I'm not really looking. We hope sometime we'll be able to look at it, but we're not come to it. So, okay, so that's all.
Nice talk. Does anyone have questions or remarks?
Yeah, is there a SER kind of conjecture for this because it's plus minus 1?
No, here this is just local. Locally, the roots can be the same. But SER, of course, SER is for all Artinian thing, which is what Froelich, Curie, and Delin have proved. So the global root number, if the representation is realizable over real numbers, then it's +1 all the time. But you can have characters which are, so Froelich has produced by a quaternion groups or other things. I have not looked at those examples. Sorry? I don't know. Yeah. No, but the conjecture of SER, at least as far as the Artinian Galois representations, it's there. That is +1 all the time for the global field. So, which one? Froelich? Yeah. Yeah, many people have. Yeah, it's Anand and Deependra who pointed out actually the relevance of this paper. Yeah.
Oh, yeah.
Yeah. No, in the sense, see, the representation breaks up as a sum of irreducible representations. So the Gauss sum will be scalars at the various factors. So then the question is, of course, the eigenvalues are, yeah, so that is pure, but it depends on kappa rho. Suppose if you have a Steinberg representation sticking in, then it brings it down. Steinberg has 1 as an in the conjugacy class. So then the multiplicity kappa rho will be contributing. So as long as you don't have 1, then the absolute values are the same. Actually, the way we got to this was sums are different from more from an analytic number theoretic point of view. We got to this because when you want to generalize some things like Polya-Vinogradov kind of theorem, where you need to work with, see, the Gauss sums, but here I've always taken the, see, I'm working with characters of MDFQ. So okay, see, one of the issues of all this beyond endoscopy or other thing is that the GLD sitting inside matrix group is extremely nice embedding with respect to which you can define L functions. But if I have orthogonal group or even SLD sitting inside the full matrix group, that's not such a nice embedding where with respect to which you can define all this Fourier transforms and other things. So that is where the difficulty seems to be. Not, sorry, I would not say that's a right concept. When the nice thing happens, you can define L functions. When that does not happen, what do you do? And you don't know what is to be done. So some of this situation is extremely special. I don't know what is the correct way to look at Gauss sums beyond these groups. And of course, I'm saying these guys, Nobauchow, Brauman, all they have some notions to look at Gauss sums beyond for other finite groups. But again, I don't know what the purity or any such thing in those cases are, how it is. Yeah.
Well, if not, we can thank the speaker again.
Thank you.